Crash Course Instrumentation, Episode 50. Coordination, Making Protection Work Together. Intro. In Episodes 48 and 49, we explored fuses and circuit breakers individually. But in real electrical systems, you rarely rely on just one device. Instead, you layer them and make sure they work together. This is called coordination. In this episode, we'll explain what coordination is, why it matters, how it's achieved in practice, and even look at how poor coordination has caused large-scale blackouts. Act 1. What is coordination? Coordination means arranging protective devices so that only the device closest to the fault opens, while upstream devices stay closed. This is also called selective coordination. Example: if a branch circuit motor overloads, the breaker protecting that branch trips, not the main breaker for the entire panel. Proper coordination keeps faults local, minimizes downtime, and ensures other parts of the system remain energized. Act 2. Why coordination matters, and a historical lesson. Without coordination, a small fault can cascade through the system and shut down much more than intended. This can interrupt unrelated equipment, cause costly production downtime, complicate troubleshooting and repairs. The NEC and NFPA 70 require selective coordination in emergency systems like hospitals and high-rise buildings. Historical note: poor coordination played a role in the Northeast Blackout of 1965, when cascading protective trips caused a massive power outage, affecting over 30 million people in the US and Canada. Although large-scale transmission issues were the root cause, the event highlighted the importance of properly coordinating protective devices to prevent small faults from triggering system-wide outages. Act 3. How devices are coordinated. Devices have time current curves that show when they will trip based on current level and duration. A fast-blow fuse may operate in milliseconds for short circuits. A thermomagnetic breaker may trip over seconds for moderate overloads. Large electronic trip breakers can be adjusted to coordinate with downstream devices. Engineers overlay these curves to ensure downstream devices trip first. This method ensures the smallest possible section of the system is disconnected. Example: branch circuit. 15 amp breaker protects the motor feeder. 100 amp breaker stays closed unless the branch breaker fails. Main service. 400 amp breaker only opens for major upstream faults. Act 4. Real-world applications. Industrial motor control centers use layered coordination. Motor overload protection trips first. Feeder protection opens only for feeder faults. Main service protection opens only for catastrophic system faults. Hospitals, data centers, and critical facilities require documented coordination to ensure life safety and critical systems remain powered during faults. Coordination also applies to renewable and distributed systems. Solar inverters, battery storage, and microgrids must coordinate their protective devices with utility connections. Wrap-up. Coordination ensures protective devices act like a team. The right device opens at the right time, faults are isolated, and the rest of the system keeps running. In our next episode, we'll apply these principles in real-world case studies to show how proper coordination prevents costly downtime and dangerous outages. Like, comment, and share to help more learners understand why coordination is key in electrical protection.